see what happens if you have a mixed endpoint condition. So if you have x of 0 as 0, but x prime of 4 equal to 0, what will be the eigenvalue and eigenfunctions? And you can actually go even more general. So if you're wondering when we get to actually use these questions, we will be using this to solve partial differential equations, which is extra hard. Harder than anything that you've seen so far, okay? In the partial differential equations, you can do something on the boundary of the material, so especially on the heat equation. At the endpoints, you may put the temperature as 0 at the endpoints, which is called the Dirichlet boundary condition, or you can put the endpoint as whose derivative equal to 0, and that's called the Neumann condition. And there's even more general one, which is, I think it's called Robin's condition, which you have a mix of x and x prime. So the endpoint condition might be like x of 0 plus x prime of 0 equal to 0. That could be another way the question could be put as. That's even more complicated. And in our case, it'll always be just this same differential equation, because this is the one that you have to solve for heat equation or the Laplace equation. That's why we will only concentrate on this. But for general case, you have more complicated form of differential equation with a different type of boundary conditions. Sometimes they have something called periodic boundary conditions, which is instead of setting equal to 0, you may have x of 0 equals to x of 4. That could be another possible boundary condition. So you have a bunch, okay? And we're just doing the bare minimum, okay? When you're taking higher engineering courses, you may end up solving a lot of these partial differential equations, and when you get there, you'll be seeing these harder Sturm-Liouville type problems. But for this course, we're doing basically an introduction to differential equations and partial differential equations. So that's why we're only doing the very basic minimum. Okay. All right, so let's try to solve this one. Solution. When we said that we're only going to do, we'll always do lambda equal to 0, one case, and another case lambda bigger than 0. And we never handle the case when lambda is less than 0, because mathematicians told us we don't have to. Okay, for lambda equal to 0, we end up with the solution always becomes a plus bt, right? And then x of 0 being 0 forces you to have a as 0, because if you plug in 0 into here, you get a. So that gives you a as 0. And x prime is just, if you differentiate this, it's always b. So regardless of the value you plug in, we have to plug in 4. Regardless of the value, it's always b. And if that's equal to 0, that gives you b as 0. What does that mean? What does that mean? If a and b are both 0, that means x is a trivial solution. Therefore, is lambda an eigenvalue or not an eigenvalue? Not an eigenvalue. So lambda equal to 0 is not an eigenvalue. Okay? All right, now we can handle the case lambda bigger than 0. Lambda bigger than 0, we will skip the part doing the characteristic equation because it's getting old now. It's always x of t, c1 cosine square root of lambda t plus c2 sine square root of lambda t. And then you plug in 0. Again, 0 equals to x of 0. Cosine 0 is 1, so you get c1 times 1. Sine 0 is 0, so c2 times 0, so that's just c1. That means c1 has to be 0. And then x prime of t x prime of t, since c1 is 0, we don't care about that. We only have to differentiate that. That's c2 times square root of lambda cosine square root of lambda t. And then for x prime of 4 to be 0, we end up with c2 times square root of lambda cosine square root of lambda times 4. And that brings us into the question, when is cosine 0? Let's look at the graph of the cosine. It's 2 pi, pi over 2, 3 pi over 2. Cosine graph goes like that, and it extends again. So what is this next step?
5 pi over
5 pi over 2, right? The next one is? 7 pi over 2, right? Okay, so when does cosine become 0?
Pi over 2, 3 pi over 2,
n pi over 2.
Pi over 2 times some number, but if that number is even, it's not 0, right?
n plus
n minus 1.
So it has to be an odd number times pi over 2. That's when cosine is 0.
n plus 1 pi over 2.
No, how do you write down that odd numbers?
Minus
1.
Okay.
Minus 1.
How do you write even numbers?
2n.
2n.
Oh.
2n minus 1.
Yeah, 2n minus 1 will give you all the odd numbers. 2n minus 1 times pi over 2. That's when this is equal to 0. So we see that in order, since c2 can't be 0, c2 equal to 0 gives you trivial solution. Lambda is not 0 because that's the case that you're dealing with. And since both of these are not 0, you're forced to have cosine as 0, but cosine is only 0 at these points. So we have square root of lambda times 4 equals to 2n minus 1 times pi over 2. And when you solve, if you divide by 4, that's 8, and when you square it, you get lambda equals to 2n minus 1 squared, pi squared, over 8 times 8 is 64. That's your lambda. Those are your eigenvalues. And this is an eigenvalue for n 1 or greater. If n is negative, you get a negative number here, but if you square it, you get the same positive number. So you don't want to list the same thing over and over again. So you should only have n 1 or greater. And then for that case, so that's your eigenvalue. Your eigenfunctions are x of t equals to some constant. Instead of writing c2, I'll just say some constant. Constant times, it's actually this one, right? This c2 times this thing. It's constant times sine of 2n minus 1 pi over 8. Those are your eigenfunctions.